Now we will talk about electric potential differences and electric energy differences and variations in an electric field. And we will start by considering a specific example, which is uniform electric field, where the manipulations and the mathematics is easier actually. But what applies here, and generally most of what applies here applies to any field, as we will see. So we will start with a uniform electric field. And by uniform electric field, as you can see, this is my uniform electric field here. Now, in this case, I want to find first what is the potential difference between point A and B. Forget about this point charge. This point charge I will take later when I consider the energy. But now I want to take about the potential. So what is the potential difference between A and B? Well, calculating this is an integral, okay? Minus integral from A to B, E dot ds, choosing a path as you go from here to here. Now, let me take a displacement from A to B path, so that the displacement, this path is parallel to the electric field lines in this case, okay? And if I do this, then to find VB minus VA, which is this integral, I want to consider this integration. Now I choose, as I mentioned, I choose the path here so that the ds's, the path is a straight line going from A to B, and therefore the ds's are always parallel to E over that path. In this case, E dot ds will be E ds cosine 0, okay? Now, E is uniform, so I can take it outside the integral. So I get VB minus VA equals minus this integral. E is constant. I can take it outside the integral. And if I take E outside the integral here, then what remains? Integral from A to B ds. But when you add up all these ds's, it is just this distance from E to A, which is d. So delta V is equal minus AD. So potential VB minus VA is equal minus ED. Now E is the magnitude of the field is constant, D is just the length here, it is also a positive constant. So E and D both are constant, so this quantity is negative. So this tells us that point B is at lower potential than point A. In other words, when you move from A to B, the potential drops. The potential drops. Okay, this is the result. Now, evidently, life became easier by my choice of path, saying that in this case, I have chosen the path so that from A to B by a line or a vector which is parallel to the electric field, and life was made easy. But remember that this integral is independent of the path. Therefore, this result would have been obtained even if I have chosen any other path. Only it would be more complicated, or probably it would be in practice impossible to evaluate, to find analytically, but the result should have been the same, should be definitely the same. Why? Because it is just the potential difference between these 2 points, okay? And this depends only on the end points, it doesn't depend on anything else. So the result that when you move from point A to point B, which are here along the one field line, then the potential drops, and this potential drop is equal minus E times D. So this is my result. So the conclusion that in a uniform electric field, when you move from along the field lines, then the potential drops. The potential decreases, or the change in potential is negative. Okay, so this is a very important result. Now, assume that point B was not, okay, it was down the electric field, but but it was not just along an electric field line, it was somewhere here. Okay, so this distance is still D, so it is at a distance D along the line from A, but of course the total distance is different now. Okay, so what would be the potential difference between A and B in this case? Again, we integrate. Now the integral is about this line here, okay, this path going from A to B. So the ds's are infinitesimal displacements along this path. So you do this. E is uniform. You can take it outside the integral. So minus E dot, because now it's a constant vector. E in a uniform field by definition. It's uniform magnitude and direction. So we can take it outside. Now dot this integral. What is this integral? It is the sum of all these displacements. What is the sum of all these displacements? Now this is a sum of vectors. Okay, vector displacement. It is just the total vector. So it is minus E dot ds. But what is minus E dot ds? It is E times the magnitude of S, magnitude of E, magnitude of S, cosine the angle between them. And what is this? What is S cosine this angle? It is just D. So the result is again delta V is equal minus ED. So even if the point B was at a distance D, but not along a field line, but so that it is in this form, then the potential difference is still the same. The meaning for this is that the potential difference between 2 points in a uniform field depends depend not on the physical distance between them, but how far they are from each other along a field line, along the field line. So the distance among their field lines. So you take this line here, you take this line here, okay, and then you find the difference between these, and the potential difference between them will be the same. Of course, we will come to this later when we consider equipotentials. The meaning of this, of course, is that point C and point B here are at the same potential. So whether you find the potential difference between A and C or A and B, it is still the same in this case. Now, we go back to the issue that, or the observation that the electric field, the potential drops or is negative or decreases as you move along the field lines. We have calculated this, and we have seen this explicitly when we considered a uniform electric field. But since this is always true, since this expression is always true, I mean this is the most general expression, then one can show that if B with respect to A is down the field lines with respect to A, in other words, the field is directed, it's not uniform. There are field lines flowing in space, and this point A, this point B. To go from A to B, you move with the field lines. So B is down the field with respect to A, even if that field is not uniform. But because of this expression, and the fact that this is not, this is path independent, then the potential drops always as one moves along field lines in any field, not only a uniform field. So this is a very general rule, okay? Again, point B is down the field lines in comparison to A. The field need not be uniform. Due to the fact that delta V is given by this expression and this minus sign, then one can show that, we will not show this explicitly, but it's almost here intuitively evident, that as you find the potential difference B with respect to A, given that B is down the electric field lines with respect to A, or down the stream if you like to think it this way, then in this case the potential will always be negative, or there's a decrease in the potential as you go from A to B. So this is the general result. The change in the electric potential, not potential energy. This is the potential. There are no point charges now or test charges. It is just the field. Is negative when we move along the field lines and positive when we move against the field. So if you go down the field or along the field lines from point to another point, then you are moving, the potential drops. The potential change is negative. That final point is at lower potential than this initial point. And it is the other way. If you move against the field lines from this point to this point, then in this case, this point is at higher potential. So what we say, we express this, we say that when you move along the electric field lines, you are moving through a potential drop. When you move against the electric field lines, you are moving through a potential rise. And this is true for any electric field. And this observation is crucial, and we will come back to this when we consider currents. Now, this is one of a couple of checkpoints in this class, and it's important that you do it. Now, what about potential energy? We have said that when you move along the field lines, you are actually moving through a potential drop. Okay? Now, what happens to the potential energy in this case? And to define the potential energy, field is not sufficient. You need another charge. You need a system of a charge and a field to define the potential energy. So let's see and investigate what happens to the potential energy in this case. So I have this system here where I have point charge and an electric field. Okay. Now, this is a positive charge. I take the power charge test charge, which is Q naught, as a positive charge. Now, what happens to the potential energy of this positive charge as you move from here to here, from this point to this point, okay, along the field lines? Well, from what we have said, it loses potential energy. Electric potential energy. Why is this so? Because what is the potential energy? The potential energy is delta U equals Q naught delta V. Delta V is negative when you move along the field. Multiply by Q, it's still negative because Q is positive. Okay? So when a positive charge moves down the field lines, this is shown in a uniform electric field, for a uniform electric field here, but this is true for any field. When a positive charge moves down the field lines, it always loses potential energy. One way of seeing this is it's very easy, because put a positive charge here, the force on it is downwards, so it will speed up and its kinetic energy will increase. Okay, its speed will increase and kinetic energy will increase. So it's gaining kinetic energy. Where does this increase in kinetic energy come from? It comes from drop in potential energy. Okay, so this is how to think of it. It's like that, putting a mass here and releasing it in gravity, and it will fall in this case, and therefore it will potential energy is dropping and kinetic energy is increasing. Okay, so this is a general result. However, when the charge, so this is what happens. Now, the field is doing positive work, but delta U is equal minus the work of the field. Okay, so delta U is negative, and this is the fact that this gains kinetic. It gains kinetic energy requires that the potential energy drops, which is an example of conservation of energy. Q is negative. If the test charge Q naught is negative, then delta U is positive if Q0 moves along the field. Okay, why? Because what is delta U? It's Q0 delta V. Delta V along the field is negative. Q0 is negative, negative times negative positive. And of course, if you have a system which consists of a negative charge, an electric field, then that system gains potential energy when the charge moves in the direction of the field. Okay, so if you have here in this, if this is a negative charge, okay, and for this, if it moves from here to here, then it is delta V here is negative, the charge is negative, so minus times minus gives you plus, so it gains when this negative charge moves from here to here. The potential is negative still, but the potential energy change is positive. So it gains, this charge gains potential energy. This negative charge or negative charge field system gains potential energy. Okay? Now, how to understand this? Well, we can understand this very easily by saying that, looking again here, this charge will not move from here to here by its own. An external force needs to act on this charge to move it from here to here. Why is this? Because the force by the field on this charge will be in the opposite direction, upwards in this case. So actually, if you relieve the charge as it is, it will move in this direction. To move it from here to here, it must be forced by an external force. But we know that when an external force does a work on a system, okay, then this leads to an increase in the potential energy of the system. This is quite a general result, and we have demonstrated this for gravity before when we made the review. So therefore, it is quite natural to understand now that as the charge moves from here to here, then definitely the change in the potential energy, a negative charge moves from here to here, the change in the potential energy must be negative because there must be an external force doing work on this charge and on the system in order to have the charge moving from here to here. And once you have an external force doing positive work on a system, then that will lead to an increase in the potential energy of the system, and this is exactly what we have in this case. This is also a crucial checkpoint to understand the relation between potential changes and potential energy changes in a field. Now, the topic that I'd like to consider now is the equipotential surfaces. Now, you remember we have calculated this expression, this integral, which is the change in the potential. We have seen that if you calculate it along this path or this path, then you get the same result, telling you that B and C here are at the same result. Actually, since S is arbitrary, then this tells you that all points on a line here, which is parallel to the, or actually it's another line here, and if you think in 3D, this is a surface, okay? Because this is in 3D, the electric field in this case is in a region, okay? So if you think of a surface that is perpendicular to the electric field lines and the A lies on that surface, and there is another surface at a distance D and perpendicular to the field also, then any vector that goes from A to any point on that surface, if you calculate the potential difference there, you will get the same result. And the meaning of that is that all the points on that surface here are at the same potential with respect to point A. Not only this, you can also show that if you let A move along that surface also, the surface here, then the potential difference between any A here and any A on that surface will be the same. And also, you can see the meaning of this is that all the points on this surface are at the same potential. All points here on that surface are at the same potential. Now, these surfaces, of course, these are hypothetical surfaces, which are in an electric field, and they have all points on that surface are at the same potential, are equipotential surfaces. That's surfaces of equal potential. Now, on these surfaces, there is no potential difference between any 2 points on that surface. That's all the points on that surface is equal to, are at the same potential. So delta V between any 2 points in that surface is equal to 0 because they are on the same potential. And the meaning of that also is that if you move any charge on that surface, then in this case, that charge also, there will be no change in the potential energy of the no charge, because delta U is Q delta V. If delta V is equal to 0, if the 2 points are on the same surface, potential surface, then delta U will also be at the same, will be 0. But to move a charge between 2 equipotential surfaces, you just multiply the potential difference between these 2 surfaces by the charge that has been transferred, and you will get the change in the potential energy of that charge field system as it moves between 2 equipotential surfaces. this is a checkpoint where you will apply this final result that I have derived. We will talk about equipotential surfaces, and we will consider more equipotential surfaces as we discuss the electric potential of point charges and other configurations. Now let's do some numerical example. One numerical example, which is the electric field between two parallel plates of opposite charge, and we will work on the field potential relation in a uniform field, and also a motion, the change in potential energy of a particle in this field. So we will generate a uniform electric field. One way of generating a uniform electric field is to consider two large plates, connect these two plates to a battery, okay? Then in the region between these two plates, away, and these two plates are separated by a distance d, which is smaller than their dimensions. In the middle here, away from the origin, okay, then the electric field can be taken to be, excellent approximation, can be considered to be uniform. So this is one way of generating a uniform electric field. We connect one of them to one terminal, the other to the other terminal, positive and negative terminal of battery. So we have here such an example. The plates are separated by 0.3 meters, and the voltage of the battery is 12 volts. That is, there is a potential difference between them now, maintained by the battery, and this potential difference is equal to 12 volts, a constant potential difference equal to 12 volts. First, I want to find what is the magnitude of the electric field between the two plates. I am giving the potential difference, or the voltage, I am giving the distance, and I want to find what is the potential, what is the electric field. Well, E is delta V over D, and I want to find the magnitude of the field, so I take the absolute value of the potential difference, which is 12 volt. D is the distance, and just I apply it, and I get, this is the expression. So it's 4 times 10 to the power 3 volts per meter. So it's about 4,000 volts per meter. Now, this is probably the first time you see this volts per meter as a unit for measuring the electric field, because we have been measuring the electric fields as coulomb as newtons per coulomb, okay? But you can show that volts per meter is exactly means actually newtons per coulomb. It's exactly the same. So just try to do a simple exercise, express what is V is, it's like joule per coulomb, and you can show that the whole thing also means Newton volts per meter, and you will see that the whole thing will boil down to newtons per coulomb. This is common when you talk about potential. Then it is common to express the electric fields in volts per meter rather than newtons per coulomb. So when you do dimensional check, try to check that in these cases, your field might be, the units of your field is volts per meter. That's also okay. Now we consider a proton, which is point charge, and it's released from the positive plate, and it goes down the negative plate, which is at a distance t, 0.3 meter away, and we want to find what is the speed of the proton. Now, as we have just said, proton is a positive particle, a positively charged particle, and therefore, as it moves down the electric field, because the potential difference down the electric field is negative, and this charge is positive, then its potential energy will drop. What will happen to its kinetic energy? The kinetic energy will increase with the same amount. Okay, so we can use this idea of this relation of conservation of energy, principle of conservation of energy, to find it out. Now, so delta K plus delta U is equal to 0. This says that the mechanical energy of the system is conserved, but this is of course true. Why? Because I have no external forces doing work. So the right-hand side here is 0, and this is the mechanical energy, it is conserved. Okay. Now, so I just apply it. Delta U is E delta V, and delta V is VB minus VA, and you solve this equation for v because it is your target variable, and you get this expression. Now, the minus sign here comes from, moving this to the other side. Now, when you substitute for delta v, you substitute minus ed. This is the important point. Why? Because, it is delta v is negative in this case. And so the whole, the square root becomes positive, and this is your expression for v. As usual, we solve, we first reduce the expression algebraically, and then we substitute the numerical values. Now, when you substitute the numerical values, you get this expression for the speed of the proton when it reaches this point.